So how are SZ effects used for science? Initially with the science of clusters. Well, the most straightforward thing is just to measure the integrated SZ effect of a cluster and then compare it with some other data set. And there's some interesting things you can get out about the contents of the clusters. With higher resolution, you can look to do some structures, and you can look to see how the SZ effect relates to the gravitational lensing signal of a cluster. I'll explain why that's interesting in a moment. So, what is the integrated SZ effect of a cluster? Well, based on what I've already shown you, it's something to do with a solid angle integral, the d omega integral, over the Compton Y parameter, which is proportional to the product of the density of scatterers, so the electron density, and the electron temperature. Now, that whole thing is proportional to a volume integral of a product of a density and a temperature, or product of a density and an energy per particle. So what you have here is a total thermal energy content of the entire object that's being described by this Srj, the flux density of the cluster. In other words, if you can measure a total flux density of a cluster, you straightforwardly get the cluster's total thermal energy content. And that means if the cluster is in any sort of settled state, you get a good measure of the gravitational potential energy, and so how much the cluster has assembled. And if you can do this for a population of clusters as a function of redshift, you could look to see how structure assembles. If the cluster is not in virial equilibrium, hasn't really settled down there yet, then you'll see it as an outlier. So again, looking at a set of redshifts, you could see a change in the scatter of the SZ effect signals. And that would tell you how much assembly activity there is as a function of redshift. A very useful thing to know. Writing that a different way, the total flux density is proportional to the number of electrons in the cluster multiplied by the temperature of those electrons. Now, very usually we look at the SZ effects of X-ray emitting clusters, and for those we can get the electron temperature from the X-ray spectrum. So, measuring the flux density tells us how many electrons there are, and if we make some rather weak assumptions about what a cluster is made up of, that tells us how many baryons there are. Now, the X-ray data also gives us a very good measure of the total cluster mass. So by comparing the SZ effect to a mass derived from X-rays, we can measure the fraction of the contents of a cluster that are in baryons. And if a cluster is a fair sample of the universe around it, then the fraction of the mass of a cluster that is in baryons ought to tell you something about the fraction of what's in the universe around it that's in baryons. And we'd expect to see this number being more or less constant over all redshifts, unless there are processes that preferentially cause baryons to drop into clusters or to be expelled from clusters. You can try to measure the structure of an SZ effect, and that'll tell you something about the structure of the atmosphere. So far, that's only been done very crudely by SZ effect data, and that's because the signal to noise of X-ray measurements is usually very much better, and the angular resolution of the X-ray data is generally very much better. So X-ray based structures are generally the gold standard. Well, that's in the center of a cluster. But as you go further out, the density drops, and the X-ray emissivity drops like density squared, whereas the SZ emissivity just drops like density. So SZ effects ought to be better at telling you about the outer structures of the envelopes of clusters, the outer parts of cluster atmospheres. Of course, you need high sensitivity to do that, but potentially that's something that can be coming along in the near future. And people have made a stab at this by stacking measurements of multiple clusters and just adding them on top of one another to try to pull up the sensitivity to the outer gas. Eventually, the hope is that one might be able to see the accretion shock where gas is dropping into the clusters for the first time and heating up suddenly, because there will be a pressure spike in those locations, and the SZ effect is proportional to pressure. SZ effects also relate rather strongly to lensing. A exceptionally good way of measuring the mass of a cluster of galaxies is to look at the distortions of the images of other galaxies behind that cluster by the mass of the cluster itself, acting as a gravitational lens. Now, what that means is that if you measure what's called the ellipticity field of the background galaxies, you can integrate over solid angle with some kernel function ki to extract a surface mass density as a function of position. So you can measure the mass through a cluster in here or there to make a map of the mass distribution. And this sort of thing is now common. If you did that also with an SZ effect map, and you assumed there wasn't a lot of temperature structure, the ratio of those two maps is a map of the baryon mass fraction across the cluster. So if baryons tend to cool more and drop in more towards the center of the cluster than dark matter, you should see a spike in this sort of a map. Now, so far, this sort of thing's only been done more or less on an integrated basis. Here's an attempt we did in 2002, looking at the cluster O 16 plus 16. What we have on the right is an X-ray image taken with XMM. And we compared masses as measured by gravitational lensing, 2.7 plus or minus 0.9 times 10 to the 14 solar masses, and by the SZ effect combined with XMM data, 2.0 plus or minus 0.1 times 10 to the 14 solar masses. And the thing you immediately notice is that the mass measurement in the X-ray and SZ is very much more precise than the mass measurement by lensing. We can also use the SZ and XMM data in another way, just to measure the gas mass, as I've shown, and that works out at 2.6 plus or minus 0.2 times 10 to the 13 solar masses. The ratio of that to the total mass is about 0.13, which is basically the baryon fraction in the universe as a whole. So this cluster seems to be making a fair sample of the matter content of the universe. It's doing it at a redshift of 0.5. So we're saying that out to redshift 0.5, clusters are still fair samples of the content of the universe. We can turn that argument the other way around and say that this measurement confirms that the fraction of the matter content of the universe that is baryons is about 13%. That has been measured also from the CMB power spectrum, as I explained earlier. You can do that for multiple clusters, and you find, as you would expect, that the measurements of the mass in the SZ and the measurements of the mass in weak lensing really agree extremely well. On the left is a set of high quality images in the SZ being correlated with a set of high quality lensing measurements, quite a tight correlation. On the right, it's a Planck subsample for which the lensing data weren't quite so good. There's more scatter. There is quite a lot of scatter in these relations, it should be admitted, perhaps because the material that's being integrated over in the Planck sample is much more than the virialized part, whereas it isn't in the other one. As I mentioned, you can measure the radial velocities of clusters, and this is particularly difficult because the spectrum of the radial velocity effect, the kinematic SZ effect, is the same as that of the microwave background fluctuations. And that limits the accuracy of any velocity measurement to about 150 kilometers per second. What you can hope to do, though, is to look at samples and then look at how the velocity motions of clusters change with redshift as structure assembles. You would expect faster motions more recently than in the past. Here's an example of how you make this sort of measurement. There are multiple points here in the SZ, and you fit that to a combination of the red line and the blue dash dotted line to make the black line. Typically, the measurements have had accuracy of only about 1,000 kilometers per second. One example where this is perhaps more interesting is if you've got an active, violent cluster-cluster encounter going on, such as this case, a car crash cluster. And here the SZ effect, which I'll show you in a minute, is associated with particular subsets of these merging clusters A, B, C and D. The picture here is of the mass distribution of the cluster as measured through gravitational lensing in the, the colour scale. If you compare that with the Sunyaev-Zel'dovich effect, you can see very large SZ effects around the CD intersection. In other words, probably where the clusters are currently colliding and have heated up the gas to an exceptional level, much higher, much hotter than the temperature you would expect for a gas in equilibrium, and at one side of B, where it also is probably falling into the overall system. The cluster A has not yet encountered the other clusters so much, and so hasn't been heated up. Down here to the south, there's some evidence that the spectrum doesn't really fit an SZ effect thermal spectrum. You can modify it by adding a kinematic term, and then you get an infall at a speed of about 3,000 kilometers per second. That is perhaps too high to be plausible. So it's possible that there are still systematic errors in the measurements. Typically, a cluster-cluster encounter shouldn't be much faster than about 1,500 kilometers per second. This could be an exceptional cluster. You can also use clusters for cosmology. I've already explained how you can get the baryon fraction. Let's look at a few other things. One neat trick is to use clusters to measure Hubble constants. And you can do this because the X-ray surface brightness and the SZ effect surface brightness, the sigma x and delta I here, scale in different ways with electron density, electron temperature and size, L. In particular, if I take these two expressions and square the SZ effect one and divide by the X-ray one, I can eliminate the electron density. And I can rearrange to get an expression that says what the size of the cluster is L in terms of the SZ effect squared, the X-rays to the -1, and the electron temperature to the -3/2. The electron temperature can be measured by X-ray spectroscopy. The X-ray surface brightness can be measured by X-ray imaging. The SZ effect, well, measured by radio astronomy. That means that for every cluster, you can measure its size. If you compare its linear size with its angular size, then you get the Hubble constant. And you can use this for each cluster individually. Here we've done it for 0016 plus 16 again. We worked out that the distance of the cluster was about 1.36 gigaparsecs. That gave us a Hubble constant of 68 plus or minus 8 kilometers per second per megaparsec. To that we added an error of 18 to allow for the fact that this cluster could be non-spherical. In fact, it looks non-spherical here. But if it's long and thin and pointed towards you, there could be a bias. And if it's flatter and on the sky, there could be a bias. You could eliminate this final error by averaging over a sample of clusters, but we were doing just one. With a sample of clusters, again, you can construct angular diameter distance as a function of redshift to create a sort of a Hubble diagram. And you can estimate the Hubble constant. You can even try to estimate other cosmological parameters. 2006 version of that previous graph shows really quite a nice scatter around the expected line, but beware, many of these studies are done with samples which are selected on a very ad hoc basis and may be biased. One survey that probably isn't biased is the Planck survey, and the Planck data set was rich enough that you could mine it for SZ effects, and a total of about 1,250 candidate clusters were found purely by their SZ effects by looking at the microwave background data. This shows where they are as the red dots against the galaxy as the big grey region, and you can maybe see little grey dots all over the diagram, which are where clusters couldn't be looked for because there are strong point sources. I talked about measuring the baryonic mass fraction for 0016 plus 16. Here it is for a number of clusters, and you get a baryonic mass fraction from all those clusters, which scatters around the cosmic value. So it all looks perfectly sensible. At that point, I will stop, and I'll finish up next time by taking you through a look at how SZ effect observations are made.